Ah, this is the Network Hunter here, or at Network Hunter on YouTube. Today's agenda, we're going to talk about, or should I say, explain multicast MAC addresses, how a switch handles multicast traffic, IGMP snooping, IGMP communication, IGMP configuration, and going to look at a few practice examples of IGMP snooping configurations and what actually happens. Multicast Explained. So I'm going to touch on unicast, broadcast, and multicast. Unicast being a point-to-point communication where a sender uses the IP address and MAC address of the receiver and vice versa. Broadcast is a single device sending communication to every other device on a particular network or subnet. And multicast, if we look at a few scenarios where multicast comes into play, it could be one device sending communication to many devices, or many devices sending communication to one device. An example would be a surveillance system where many cameras send a video stream back to a network video recorder, or where you have a many-to-many communication when a video over IP system can have multiple transmitters sending streams to multiple receivers. Excuse me. So here, now that we know the different types of communication, let's understand how these devices communicate in broadcast or multicast scenarios. These devices will need to use IP addresses and MAC addresses for layer 3 and layer 2 communications. So the general inquiry broadcast IP address is 255.255.255.255. The general inquiry broadcast MAC address is Foxtrot, 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 and so on, which is hexadecimal. An example of a broadcast address for a 192.168.1 network on a /24 and its subsequent MAC address is, so the broadcast address for a 192.168.1 network would be .255. That goes to every host on that network. And then the MAC address again will be all Fs, which is hexadecimal. An example of a broadcast address for a /16 10.10 network and its subsequent MAC address would look like this: 10.10.255.255. So that's going to all the hosts. That's where you get the 0 through 255. It's 256 bits that have to be accounted for, or 256 IP addresses. And 0 counts as an IP address. That's why you get 0 through 255 versus 1 through 256. That's why you see the number 255. The most common ranges that you'll tend to see are probably going to be a 224 multicast IP address or a 239 multicast IP address range. So if you look at this, multicast IP addresses go anywhere from 224 to 239, and that would be like a 224 on a class I was gonna say a class C, on a /24 to a 239 on a /8. Um, Addresses in the range of 224 on a /24, they're not routable, but designated for multicast on a local subnet only. Some of the protocols that are in use are multicast domain naming service, internet group management protocol, and open shortest path first, which is, and RIP. Address in the range of 224.0.1.0 to 224.0.1.255. Those are routable on the internet and designated as the internet control block. Protocols like NTP are used there. Addresses in the range of 239.0.0.0 to 239.255.255.255. Those are routable, but they're designated as private or local ranges for different applications. Some well-known multicast IP addresses, if you just take a quick look, you have OSPF showing at 224.0.0.5 and also 224.0.0.6. You got EIGRP at 224.0.0.10. You got PIM, IGMP version 3, NTP, which is Network Time Protocol. So all these are well-known multicast IP addresses that you're going to use if you're trying to use one of these protocols in a multicast situation. Multicast addresses or multicast MAC addresses explained. So multicast MAC addresses have a reserved prefix, and that prefix is 01005E as in 5 echo. It's just the first half of a MAC address. All right. The first 24 bits essentially is the reserved multicast MAC address prefix. The full 48 bits is the full multicast MAC address or any MAC address. Now, when we look at multicast IP addresses or any IP address, there are 4 octets. In this case, we're going to reference them as A, B, C, and D, or Alpha, Bravo, Charlie, Delta. Each octet has 8 bits in it, and there's 4 octets, so there's a total of 32 bits in an IP address. A MAC address has 48 bits. Okay. If you look at these numbers 1, 2, 3, and 4 at the bottom, this is going to be the process we're going to use to show you how to derive the multicast MAC address. So again, the reserved multicast MAC address prefix is 01005 echo. First 24 bits of a 48-bit MAC address. Now, we're going to look at a conversion example. We're going to use the multicast IP address 239.255.1.6. First thing we want to do is convert that multicast IP address to binary. Okay, you can see that nomenclature there. Next, take the reserved multicast MAC address prefix, which is 01005E, and replace that entire first octet of the multicast IP address with it as such. So now you have this binary nomenclature, and you take that whole first 8 bits, which is the first octet, which is letter A. When we're talking about the nomenclature that we're using for the IP address variable, and when you apply it, now you have 01005 echo, and then you have all the 1 bits turned on for the second octet, which is 255. You have 1 bit turned on for the third octet, which is just the number 1, and then you have 2 bits turned on in the 2s and 4s column, which gives you 6 bits turned on in the fourth octet. So the last couple of things that you want to do is you want to replace the 24th bit with the binary bit with a 0. So it is initially a 1. So you want to, in this situation, you want to convert that with the 0. You count from right to left to get to the 24th bit. Okay. When you get to that 24th bit, you'll see it's a 1. All you got to do is erase it, convert it to a 0, as you can see There it is in red. It's been converted to a 0. Last, you want to convert to hexadecimal to create the multicast MAC address. So what you'll get from that now is 01005E7 Foxtrot or 7F0101. Well, actually, I'm wrong on that. It's not 0101. I actually wrote that wrong. It's actually 01, and then the last one should be, so these first 4 bits are 0, and then the last 4 bits are 6, so it'll be 0106. So that's a error on my part, not 0101, but 0106. All right, so now, how does a switch handle broadcast traffic? Right? The switch will flood block broadcast traffic out of every one of its ports because it needs to know how to get to every device connected to it. How does a switch handle multicast traffic? Well, initially it does the same thing. It floods out the traffic out of every port until it registers um, where the traffic is coming from, and then it essentially is going to document that uh, source in the MAC table, source address in the MAC table. So one thing I want to talk about is for the switch not to flood multicast traffic, we must enable IGMP snooping for the VLAN or subnet. Um, and explaining again, why does the switch flood the multicast traffic? It's because the switch floods the frames when there is no entry in the MAC table. The switch builds the MAC table based on the source MAC address. Because there are no devices sourcing traffic with multicast MAC addresses, the multicast MAC addresses can't be found in a normal MAC table. So when you enable IGMP, the switch builds another table for multicast traffic with multicast MAC addresses. So IGMP snooping. IGMP manages multicast group memberships based on a query and response mechanism. What is a multicast group? It's just a set of devices that send or receive the same multicast data. All devices in a group use the same multicast group IP address. So you ask, how does IGMP control the multicast traffic and prevent it from being flooded? IGMP uses a mechanism based on the query and response. All right. Devices on the network that support IGMP will either join or become a member of a multicast group. The switch or router sends periodic queries to these groups and receives responses, and accordingly, the switch decides where the traffic goes and when it should stop receiving it, or should stop the traffic from going out to those devices in the group that left. There's 3 versions of IGMP, version 1, version 2, and version 3. We won't really talk about the differences here on this particular session. Just know that all these versions are backwards compatible, so a router, a layer 3 switch supporting IGMP version 3 can support client devices running version 1, 2, or 3. And know that IGMP is a layer 3 protocol. All right, so here, IGMP messaging. So the query and response mechanism. So this device, video receiver 2, sends a join request. Okay. excuse me. So talking about the mechanism for the query and response, you get a report slash join, you get a query, you get a leave request, and then you have your group specific query. So a general query, I'm just going to talk about a couple of different types of queries. So a general query, um, a message is sent from the querier, which is either a router or a switch, to get an update report from all devices sent every query interval time, which is like 125 seconds by default. Um, and that multicast IP address for a general query is 224.0.0.1. Another type of mechanism is the group specific query. That happens when a message is sent from the querier, the router or switch, asking for a response from each host belonging to the multicast group. All right. So in this situation, if you look at this MOIP switch in the middle, if that MOIP switch were to send a group specific query to the video receiver 2 and video receiver 1 on the left, it basically asking for a response like, are you still there? Do you still want to receive traffic? If those devices don't respond in 125 seconds, the stream or whatever it is, that traffic will stop being sent to them. If they do reply, I'm here, you keep sending out that traffic, that multicast traffic to them. Okay. Now, a report or join mechanism, that's sent by a host to the querier to indicate that the host wants to be or is a member of a given group indicated in the join message. For IGMP version 2, that's the group multicast IP address. For IGMP version 3, that multicast IP address is 224.0.0.22. And for the last mechanism I'm going to talk about is the leave mechanism. It's a message sent by a host or a device to the querier to indicate that they no longer want to be a member of a specific multicast group. That multicast IP address is 224.0.0.2. Here we go again. General query. Sent every query interval time. That query interval time by default is 125 seconds. The general query, which comes from either a router or a switch, sends out that query using multicast IP address 224.0.0.1. A group specific query is sent to a specific port when receiving a leave message on that port. Okay. That uses the group multicast group IP address. A report or join mechanism for IGMP version 2 again uses the group IP address for multicast. For IGMP version 3, the multicast IP address used is 224.0.0.22. The mechanism to leave a multicast IP group uses 224.0.0.2. Here we're going to look at some packet captures. You'll see the top one in red, the next one in a orangish red, and then the next one in green from the top. So if you look at the first one, you'll see that it's a general inquiry from 10.0.0.5. And we know this because its destination IP address or multicast IP address is 224.0.0.1. The next one is a leave request from 10.0.0.68, and we know that because the multicast IP address is 224.0.0.2. Lastly, we get a membership report from 10.0.0.145. You see that in green because the multicast IP address being used is 228.1.0.0. Again, this is just shown in a packet capture. And also, if you look to the right, You can see the descriptions in the packet captures. It tells you membership query, leave group, membership report, etc., etc. Even if you look at this one on the bottom, you can see IP address 192.168.0.110 is initiating a leave request from the multicast IP group, and it's sending it on. We know this because it's 224.0.0.2, and it's leaving group 239.1.1.101. IGMP configuration. So again, there's a few different versions, 1, 2, and 3 for IGMP. As far as the querier status, if you're active, you are the querier, meaning that you inquire, you ask questions. And if you're passive, then you just kind of just, I guess, pass traffic, I guess is what you call it. There's the fast leave command for IGMP version 2 and the tracking command for IGMP version 3. And then you have your IP multicast disable flooding command, and we'll get into a few of those. So technically, when a device receives an IGMP version 2 leave message, it sends out multiple group specific queries. If no other client replies within that waiting period, the device stops forwarding traffic. When the multicast fast leave version 2 command is configured, again, when the multicast fast leave version 2 command is configured, and when that device receives a leave message, it immediately stops forwarding to that port. And when it says, when I mean by when that device receives a leave message, it's coming from the host device. So for in this example, it'll be video receiver 1 sends a fast leave request back to the MOIP switch here in the center, and traffic stops immediately. With the disable flooding command, it's a global command to disable the flooding of unregistered multicast traffic for the IGMP enabled VLAN or network. Now, when we look at a few practice questions here or practice scenarios, if no IGMP is configured, where would the stream go, leaving from video transmitter 1 on the far right using multicast IP group 239.1.1.29? If IGMP is not configured and this traffic hits this switch in the middle, what happens? Well, we went over it already. It's going to flood out of every port on the switch. Okay? Just like that. Goes everywhere. Broadcast out all ports on the switch. Now, here's another situation. If we have a multicast version 2 and then we have no active querier set up, so it's just passive on this particular switch, where would the stream go? Well, depends on who's subscribed for it. So in this case, receiver 1 is subscribed on to that group at 239, that multicast IP group 239.1.1.29. So then you'll see that the traffic, boom, will go to video receiver 1. Here's a little question popped up about what happens after 125 seconds after a general inquiry. Well, that's the default. Traffic will stop being sent to the device in that group if it doesn't reply. And to get a little bit more technical, so after 125 seconds, the router or switch sends a general inquiry on multicast IP address 224.0.0.2 to the members of the multicast group. If no reply after a few minutes or after a few inquiries, then that non-responsive device is removed from the membership. Now, here's a situation where you have multicast version 2, IGMP multicast active, which is letting you know that the switch is going to be the active querier. It's going to be asking a question. Are you part of this group? What's your status? That type of stuff. We're using multicast IP group 239.1.1.229. We have receiver 1 subscribed to that. Where would the stream go? Obviously, it goes to receiver 1. The stream will stay until the receiver 1 sends a leave message to stop streaming. But in this case, it doesn't show that fast leave is configured. So what actually happens is that the general inquiry will keep being sent out and this device won't respond anymore. And then after the default interval time elapses, essentially that device is going to be dropped from the multicast group and no more traffic will be sent that way. All right. Now, vice versa, if you configure multicast with fast leave on version 2 of IGMP, when this receiver 1, video receiver 1, initiates the leave, all right, what's going to happen is this switch, this active querier, is going to get it and immediately stop forwarding traffic to that device. Okay. Excuse me. Here's another case. You look at the configuration. Receiver 1 and receiver 2 subscribe to the multicast IP address group 239.1.1.220, and it says, what if RX1 leaves this group? Well, I see fast leave configured, so the minute it requests the leave, it's going to get dropped. No traffic's going to go to it. The traffic will still go to video 2, video receiver 2. I'm sorry. Now let's get into one of the last commands we'll be looking at, the multicast disable flooding command. And why would we need to add this disable flooding command on a video over or media over IP switch? All devices on that switch understand IGMP and they use registered multicast. The command won't help in any way. The benefit of having the disable flooding command on the switches, on all switches, is unregistered multicast is being dropped by all the switches. So traffic like multicast domain name service is not being broadcasted everywhere.